My name is Evan Bentz, and here I am at the University of Toronto. I've been a professor here since the year 2000. My background is I grew up in Thunder Bay, Ontario, in Northern Ontario, and moved to Southern Ontario to go to university, as many students do, and went to the University of Waterloo, which is a fine school, but not this one. And then when I finished that undergrad, it was 1994, and I came to the University of Toronto to do graduate work, and started a master's and finished a PhD, and they wouldn't let me go. And so as a result, I'm still here. And so I've been teaching now for 13 years. Working at the university, of course, they say that there's three different components to it. There's teaching, there's research, and administration stuff. And I think the most important of the three is the teaching part. And indeed, I think the research part is actually part of the teaching, because we're basically teaching people all around the world what we've done, rather than just teaching the students that are in the room. Right now, what do I teach? I teach survey camp. I've done that each year that I've been here, which is good fun between second and third year. I teach the graduate course, finite element analysis. I also teach the second year course, structural analysis 1, that the undergrads take. Last year I taught structural analysis 2, the fourth year course as well. And I also teach a third year course that the engineering science infrastructure option students take as well. And so that's the teaching side. On the research side, what's my interest in research? The interest that I've got is understanding how structures behave. Primarily reinforced and pre-stressed concrete structures. That happens to be where my focus was from the beginning. And the idea is to understand how they'll respond to an earthquake, or to extreme loads, or to wind, or anything else along those lines. And to which one might say, well, of course we already know how to do that. We've been designing buildings for millennia. So what is there to know? Well, the trick is, if we're going to analyze things in a linear elastic way, assuming the material properties don't change, we know how to do that. But if we account for the fact that concrete cracks, and that we have shrinkage, and we have creep and relaxation, and steel yields, and things like that, we end up with a nonlinear behavior. And to understand how a structure will respond to an earthquake when the ground's moving back and forth, you have to properly be able to model these things, otherwise you won't properly understand how strong the structure really is. So my goal is to better understand the behavior of structures, and so that involves things in our lab, in actual experiments, and we compare them to our models to see how well things work. And it also then includes code-based rules as well. Basically, how do we come up with systems of equations that practicing engineers will use to decide what is good enough? And so I'm specifically looking at the area of shear. So the equations that we use in Canada for the design of buildings, the shear strength equations, are based on work that I've done here at the University of Toronto. Those equations are now also used in Canada for the bridge code as well, the United States for the bridge code, and with the new European model code that will be influencing codes around the world. I've heard a rumor that perhaps the Australian code, the Australian bridge code, is going to be using my equations too. So that's what I'm saying, that the idea that teaching actually goes around the whole world. So basically there are professors in Europe right now who are explaining the methods that I've developed, and so that's part of teaching as well, actually, to the students in other countries. One of the questions people ask is, what is the impact of the research? How does it actually change things? Because if in fact we're writing reports, putting them on the shelf and leaving them there, that'd be useless. I mean, students would learn things, but that's not good enough. So the way the people are impacted is multiple ways. One way is that we train students. Graduate students learn how to use methods that are beyond those that are in the code. They go off to industry and professorships around the world and teach other people how to do it. So that's one aspect of impact. Another key one is directly through the codes of practice. So those are the rules that we use to decide what structures need to contain in them to make them safe enough. And so that's impacted directly, that there are changes in rules that result in additional reinforcement levels being required compared to what they had previously been. And so they're actually putting in more steel into the building to make it work properly. That's all good. And there's also the aspect of individual sort of direct questions. Engineers in Toronto and around North America who I've been involved with have some structures that are giving them problems, whereby the original design may have had a mistake, or the construction had a problem, or the materials weren't good enough, or there's a change in use, and the original design doesn't actually meet the rules anymore. And so the question is, should the structure be taken down? Should the structure be evacuated and everyone removed and hidden someplace else? Good questions. And to answer these sorts of questions, most of the time the engineers in practicing firms across Toronto can do it by themselves. They don't need our help. But there are occasions where the problems are too complex and we need to use more advanced tools. And so recently I was involved in I can't tell you what it is, but a structure that is in the city of Toronto that is used by 250,000 people per day, that required some analysis to determine whether or not that structure needs to change. And I can't tell you the answer either, but all the same, it was an interesting analysis to try and answer questions about structural safety. So we are impacted as the citizens basically on the idea of, are our structures safe enough and how much do they cost to make? Anybody can make a structure being perfectly safe. It's just it costs so much that people can't afford to do it. Something like the pyramids in Egypt, the famous pyramids, will never fall down. but they were also so expensive to make, in a sense. I mean, they lasted 5,000 years so far. The Pantheon in Rome has lasted 2,000 years so far. That's pretty good. How long will the CN Tower last? Good question. It was designed to last 300 years. But we want the structures to last a whole long time and be safe the whole time and be inexpensive. And that's the third point, is the hard part to do it, actually. Now, we didn't focus extensively on inexpensiveness, because if we make things too inexpensive, they won't work very well. And it's better to spend 10% more to actually make something that'll last through earthquakes. We've learned that recently with the earthquakes in Japan and New Zealand and other places. But we want to make sure the structures we have are solid and last a long time. And that impacts society, because when you walk around through the streets of our cities, and we walk through Shanghai and look at all the buildings around us, we want them not to fall down. At the same time, we want them to be there, and they impact us. So the structures and the infrastructure that we build as engineers, as civil engineers, affect us every day. Other impacts that I've had in terms of software that I've written a number of computer programs, one of them called Response 2000. That program was finished as part of my PhD, and last time I checked, it had been downloaded now by 45,000 engineers and researchers in 155 countries so far. Anyways, I have had downloads from all around the world and keep on getting good questions. And it's another aspect of teaching, in my perspective, because the program is set up to make it easy to analyze what's a relatively simple problem. It's something that we learn in the basic use of the program. It's stuff we learn in our third year concrete courses. But it includes a lot of stuff that is really graduate stuff. And so if you're looking at some of those challenges of figuring out how strong something really is, this program goes beyond what the code does, although it's compliant with the code and it's consistent, and allows you then to evaluate things in a way that makes a lot of sense. But I wrote the program specifically so you can see all the results in a way that is, visually it looks kind of nice, but additionally it allows you to actually test your knowledge, to make sure that the individual things you think are going on are happening. So all the numbers are available, and you can put them all into your favorite spreadsheet and examine them to make sure they make sense. And so this is an aspect of teaching as well, actually. And it's been used, I've been told, in a number of famous structures around the world that you've probably seen. I've also written other software, a program called Augustus, and it's compatriot Augustus 2 now. And these are finite element post-processors and finite element analysis programs themselves that allow us to analyze 15-story buildings, accounting for all the nonlinear things that I was talking about before, yielding and cracking, all those sorts of things. That kind of analysis is possible with other tools, but it's difficult to analyze an entire building. Subcomponents of buildings we can do, no problem. But for an entire building, not so easy. And this tool is one that's currently under development that will allow us to do that, and we're having some good success with that. If people want to learn more about the research that I've got, the best way is via the technical papers that I've written. Amongst the best ones are in the American Concrete Institute Journal, so you can search in there for my name, Bentz, and have a look. With Professor Collins' help as well, and Frank Vecchio, we're going to put together a new version of his pre-stressed concrete textbook, and that'll be the best place to see everything all pulled together into one summary form. But that's not done yet, so for now you need to see things via the technical papers.